Okay, so we're almost there in terms of the materials of this class. So last time we talked about Fourier expansion. So the idea of the Fourier expansion is that although we're interested in functions of this form, which is something like 1 to n, we started from the sine expansion, sine, let's say nx, and we're interested in the domain from 0 to pi. So we learned that there is a fundamental difference between expansion with an infinite number of basis functions and the following expansion, which is a finite order truncation. So viewed from linear algebra, and if we form a vector space, V, so that it is given by all the functions fx that can be expanded into, that can be expanded like this. So let me duplicate it here, where fn is in R. Then this kind of functions, this is a fundamentally a finite dimensional space. So this is a finite dimensional space. Any function must precisely take this form. It's like up to capital N number of sine functions added together. If you give me some other function, let's say a cosine, or give me x squared, I mean, modified to satisfy the boundary condition that they should vanish at 0 and pi. Unless it really looks exactly like this, other functions just won't fit into V. However, using the Fourier expansion, it says that this case is dimension V equals to n, but the Fourier expansion concerns the case when n goes to infinity. All of a sudden, we found that as we measure the convergence, let's say in terms of the pointwise convergence, a lot larger class, a much larger class of functions, which doesn't look like linear combinations of signs at all, like the head function or some other functions we're going to see in this class, they can all be represented exactly using an infinite number of signs. So the problem is that how to compute Fn. So this coefficient we talked about two ways. If V is a finite dimensional space, which is to solve linear system, this really doesn't work because we don't know how to do Gauss elimination in an infinite dimensional setting. Or two, we start from an orthogonal basis. And this one, we can just compute the coefficients using inner product. In particular, we have learned that if we consider a general interval without loss of generality 0 to L, and fx satisfies f0 equals to fl, so it's a 0, and then you give me any function that satisfies this, I can expand f using the sine series before, and this is 2 over L, 0 to L, and this is n pi divided by Lx, fx dx. The reason why you can do this is really because this one, they form an orthogonal basis. This weird factor L over 2 here, it really comes from normalization. Namely, the inner product of sine with itself must be exactly n. The two n's are the same, otherwise it's 0. That's why it's orthogonal basis. It's L/2. So that L/2 appears in the denominator, and therefore this is 2/L. Any question? So similarly, we considered functions that satisfies the Neumann boundary condition. So prime L equal to 0. Such kind of functions, of course, they also form a vector space of itself. And the corresponding expansion takes the form. Now I'm going to slightly rewrite it in the sense that I write it deliberately as f0 divided by 2. I'm going to explain. And this is 0 from 1 to infinity, fn cosine, and this is n pi divided by Lx. So because the normalization condition, cosine and cosine, their normalization is L/2, but if n is 0, then the normalization is L instead of L/2. So I get rid of this 2 here to reflect this difference. Then I can use a unified formula. So this is L/2, 0 to L. This is cosine n pi x fx dx. Here n can be anything, any integer that is bigger than 0. And before, if you take n equal to 0, sign becomes 0. So that's not an eigenvector. So n must start from 1. So this is what we learned last time, which is the sine transform and the cosine transform. Today, we're going to go one step further to discuss the Fourier expansion of more general periodic functions. So what is a periodic function? The idea is very simple. It's exactly the same as the periodic function you might have heard before. That is, you give me a function fx if I know that there exists a number called t, where t, the name is called its period. So that this holds for any x in R, then fx is so-called a periodic function on R. And this period may not be unique. And what we are interested in is to find the smallest period of a given function. So let me give you an example. First, we start from some trigonometric functions. Let's say cosine. This one we definitely know. There is a period. So cosine function look like this, extends all the way to infinity. And we know that this is 0, and then the pi/2, this is going to be 0. At pi, this is going to be -1. At the 0, this is 1. And at the 2 pi, this becomes 1 again. So we have identified that indeed, if you take any point from 0 to 2 pi, and I go from here, add 2 pi, I get exactly the same value. I subtract 2 pi, I get exactly the same value. And there cannot be any period that's smaller than that. So t is 2 pi. So this is example 1. Let's look at the example 2. And let's say I pi x. How do I figure out this thing? So first of all, I mean, we can use, let's say, the Euler formula. And this is I sine pi x. So we know that, so the period of this thing is really 2 pi. So we can verify that x plus 2. So this is really cosine pi x. plus 2 pi. Similarly, the sine function, the period is 2 pi. So adding 2 pi doesn't do anything to cosines and sines, because here we have just shown that for cosine, the period is 2 pi. So this is cosine pi x plus I sine pi x, and therefore this is exponential I pi x. So the period t is 2. Any question?
Does this have to be true for all values of x?
For all values of x, that's right. Any other question? Okay, so the third question, the third one is a little bit more exotic, and we consider fx defined to be x minus n, where x is between n and n plus 1, and n is any integer. Okay, what the heck is this? So it's easier to see the plot. So with n, 0 is the integer. If x is 0, this is 0 minus 0, so this, I start from 0. Then between 0 and 1, so this is actually include 0, exclude 1. This is just x. But since for 1, this is not defined, I need to exclude that. So I use the empty circle. Here I use the filled circle here to indicate that when it is equal to 0, it is actually 0 here. When x is equal to 1, I go to the next branch, because now it becomes a 1 from 1 to 2, include 1. Then this is x minus 1 again, so it becomes 1 minus 1 is 0. Similarly for 2, goes back again. And for minus 1, the story is exactly the same thing. So you can see that this is obviously a periodic function, because you can check that for any point, I just plus 1 or minus 1, this is exactly the same. So t, the period, is 1. Any question? For fx is the absolute value of sine x, might say, well, didn't you just say, I mean, this is a period that's 2 pi, yeah, I mean, 2 pi is a period, but I mean, we want to find the smallest one, smallest t, so that the previous fx equals to fx plus t wholes. So again, we make a plot. We found that this is 0 and this is pi, so this is sine x without any problem. From pi to 2 pi, it was supposed to go down like this. However, now because of the absolute values, it goes up. And similarly, it goes up here, and we found that the smallest period here, t, is actually pi. So these are just a few examples of periodic functions. Any question? So before I proceed to talk about the Fourier analysis for general periodic functions, I'd also like to ask whether there are logistic questions.
I have one for the quiz.
Yeah.
So on the email it says we have an hour. Does that mean we have to submit like all our scanned papers by the hour? Do we get a grade?
That's correct.
Okay, thank you.
And from what I look at the quiz, an hour should be more than enough.
So the email said that for folks with DSP that have like time and a half or 2 time, we just go until that amount of time. Do we need to send anything?
You have a letter and you don't need to submit anything, and we have the record, and you just if you have 150 and you submit within 90 minutes, if you have 200%, and you just submit within 2 hours.
Okay.
Any other question?
Sorry, you could go ahead.
Okay, thanks. I was wondering, so for the quiz, say we submit like maybe a minute late, will that affect our score?
So there will be a little bit, grace period within reason. So let's put it like that. Obviously, if you're half an hour late, it doesn't work. But I don't want to put a very hard. But there's 1 minute probably is okay. So yeah.
And in terms of the types of questions, it'll be around the same format as the last quiz,
Yeah,
correct?
it will be the same format, and I expect the final to be of the same format as well. So that's actually the whole point of the quiz, which is to get all of you to be familiar with the format. Any other question?
Is the quiz difficulty indicative of the final difficulty, or is the final going to be harder?
No, the final hasn't been made yet. As I said, the quiz was more for you, for the GSI, and for me to get used to the format and see whether this system will work at all. How to deal with the final is pretty crazy. And yesterday, I still received emails saying that there are some discussions at the campus level talking about things, and that might affect this course. And so I'm really struggling as you are as well. So, but I just want to stress again that the quiz, at least up to now, was mainly used to test the system. It doesn't indicate the length of the final, and the difficulty also needs to be revised in the next week or so.
One last question. I don't remember if you specifically said what sections the quiz will be tested up to. Could you clarify that?
It's on GitHub. So it's
okay, perfect. No worries. I'll check that. Thank you.
Yeah. Any other thing before we move on with the material?
There's been a lot of emails about an oral exam.
Yeah.
So that's going to be separate from the final, but also required?
Yeah. So for anything regarding the oral exam, just wait for my email. And that might come really late. Any other thing? Okay, so we're going to proceed. So Fourier analysis, simply speaking, at least to this level, is to deal with expansion for periodic functions. You give me any periodic function, I'll be able to expand it to some extent using sines and cosines. Any function. Okay, it's a very strong statement. Even weird looking functions like these things and these things, I can expand it using sines and cosines only. Especially this. How would you use sines and cosines to do this? So this is what we're going to deal with. Without loss of generality, so we consider the interval, let's say minus L to L. Because it's just the interval, it's a periodic function, and I can say any interval to be take any interval so that the period is 2L. So now I would like to consider a basis. So my vector space is the following. So fx equals to fx plus 2L. Okay, so this is indeed a forms of vector space. You add the two things together, it's still, and you multiply. It's still like that. This vector space will turn out to be too large because I didn't specify anything about the continuity or the smoothness or other things of f, this is going to be definitely way too large. But since we're mainly concerned about the linear algebraic properties, so this is good for now. I would like to consider a basis of it. Again, the word basis needs to be taken with a large grain of salt if you really know more advanced materials. But again, from the linear algebraic perspective, it works so far. So we consider a set of functions, B. So this B are the following. I simply merge the functions we have learned so far. We have the sine function. I put a cosine function. I put a sine 2 pi x divided by L. I take cosine 2 pi x divided by L, so on and so forth. Okay, so all the way to infinity. Now, you give me some function f, some good function. So some good function f that is in V. I would like to expand fx using this so-called basis. How would I figure out the expansion coefficient? Because later we're going to verify that this is an orthogonal set. So I just take the inner product between f and these basis functions, and you will find that the way how we do the calculation is exactly the same thing. So I have an a0 over 2, and then I have the sine part, an, and this is, sorry, I have the cosine part. So this is n pi Lx, and n from 1. That, so Bn, so A here, again, the over 2, the factor 1/2. I have explained that before. And this is sine n pi Lx. So this is, you can think, the form of functions we want to consider. Now let's verify that B is indeed an orthogonal set. Is an orthogonal set of vectors. So first of all, I would like to verify LL. This is sine m pi x divided by L, and this is sine n pi x divided by L dx. So what's this? So this one really is nothing but, this is odd function, this is odd function. So it's a factor of 2. I can just convert that from 0 to L. And we have this. So this one we have actually seen, right? This is exactly what we have computed before for the sine transform. Other than that, there's a factor of 2 here. So if you remember the calculation, this is 0. If m is not equal to n, m and n cannot be both 0. And this is m equal to L, and this is m equal to n, but this is not 0. So this is the first part. The second part is, let's say I make some cosine, cosine. Cosine n pi x divided by L dx. So this one, so cosine is an even function. Cosine is an even function. So you put them together, this is still an even function. We do exactly the same trick. And you find that this one is really exactly the same thing as we did before. So again, if m is not equal to n, their orthogonal should be 0. If m is equal to n, but this is not 0, so not they cannot be 1, then this one is L over 2 times 2. This is L. And finally, if m is n equal to 0, this is just L times 2, so this is 2L. Any question? So again, pay attention to the constant term. And finally, we need to verify that the sine and the cosine, this inner product, it should be 0. But this is easy because this is an odd function. This is an even function. An odd function times an even function is an odd function on a symmetric interval. So this is just 0. So indeed, the B is an orthogonal set, and we have computed their normalization constants here as well. Now I can just use what we had before. So this is 1 over L, not the 2 over L anymore. This is from minus L to L, not from 0 to L anymore. This is cosine x L dx, where n is from 0. Bn is again, let me also stress, this is 1 over L, 1 over L. And this is again integrating from minus L to L. The blue is to indicate the difference from the sine and the cosine transformations respectively. And here n is starting, n starts from 1. Any question? Okay, so before I proceed, so why don't I show you a few examples first, and then we proceed. So okay, so let us look at the Julia notebook that I showed last time. Last time I really used the sine transform to show you the hat function. This time we're going to show a few more general examples. Some of you might have already seen this on the GitHub. The first one is a step function. So a step function is, here I define from 0 to pi, this is 1, and from minus pi to 0, this is minus 1. So the function looks like this. Okay, here's a step. And then the period just repeats. So the period is really 2 pi. Now, what I want to do is to compute the Fourier expansion using the method we just talked about. It's a very mechanical procedure. Once you have identified the period, which is 2L, you restrict it to the interval from minus L to L, and literally just close your eyes and compute that integral. And that's it. You get whatever you get that, you get the series. And later we're going to do an analytical derivation as well. But now let me just show you how this kind of a weird looking series how do they actually perform? For this one, because it's an odd function, I actually, yes, you can possibly imagine only the sine series would survive. Indeed, I'm going to expand only using sine functions. If I use only one term, then there's only one sine function. You can kind of like imagine in your head how this thing performs. So you want to have one sine. It cannot be too large. If it's too large, the error is going to be too large here and too large there. Although the error will be smaller here and here. It cannot be too small because the error will also be very large. So this one kind of minimizes the error. And this is the error, which is like order 1. If I use 10 terms or 11 terms, it looks much better, especially here in the middle. What it does is to use a lot of the signs and they just to do the linear combination to mimic, try their best and to mimic a step function like this. And because of odd function, it does a reasonable job here. It overshoots here, okay? This is a very important phenomena in numerical analysis. It's called the Gibbs phenomena, but this is definitely way beyond this class. And what I'm gonna say is, as you increase the number of terms, the approximation in the interior becomes better and better. In the mathematical language, it means that all of these points here, they converge in a pointwise sense. And again, there's some overshoot. This overshoot would persist even if you use a higher and higher terms, number of terms, and the accuracy here becomes better and better, but still you have a little bit here, and it goes on, and so on and so forth. So even with let's say 190 terms, here's almost perfect, but you still are gonna have a little bit error here. So this is how it works for a step function. Hopefully this is an example, to show you how powerful such kind of expansion is, even though the linear combination of the sines and cosines intuitively don't look like a step function, a discontinuous function at all, but they can very well approximate this kind of functions. Next, you might say, we used the 90 terms and got a okay solution, and here the error is about 0.01-ish or so. You might say, maybe discontinuous functions, that's way too much. If I allow the functions have a little bit more derivatives, whether the convergence would improve. If you really think about that, then congratulations, you're really along the right track. Let's just consider a function that's slightly better, which is absolute value, and I consider the interval from -1 to 1. Here, this is an even function. If you use one term as a constant, here's the term number is a little bit wrong. So it should be +1. So if you use one cosine, then it looks like this, okay? So it's not just a cosine, it's a shifted cosine because it starts from 0. Indeed, you can see intuitively, this is the best you can do with only one cosine. And the error is already much smaller than before, and it's globally bounded by 0.1. I use 6 terms, you can see the performance is really good. Other than these points here, just like the Mexican hat function, the error has already reduced by order of magnitude. When I use 20 or 46 terms of the cosine, by eyeball norm, this is very, very good, and only have a little bit of error, which is about less than, almost like 0.2%. But in the middle is even much less than 0.1% of the error. So this is like for a function, well, that is continuous, but its derivative is not continuous. Or we can say this function is piecewise continuous. Now let's consider really a smooth function. So this is a function which is a period 2 pi, and I consider a function which is the composition of a sine and a sine. How does it look like? It looks like this. It's not really a sine or the cosine. It's a more complex functions. Now, what I'm going to do is to expand it using this Fourier series. Using the Fourier series and using one term, and you can see that, the error is already pretty good. With the 3 terms, the error is already like less than 0.1%. And with the 7%, the error is like 7 terms, the error is like 10 to the -8. With 9 terms, note that I only added 2 terms here. And with 9 terms, here is already 10 to the -11. So indeed, as the smoothness of the function becomes better and better, the Fourier series also the performance of the Fourier series becomes better and better. Any question? Okay, so now let me say something. First of all, we want to make a connection with sine and cosine transforms we have learned before. So this one is really related to whether the function, which is of period 2L, is an even function or an odd function. First of all, if f is an odd function, it means that, first of all, it is of a period 2L. Second, fx equals to minus f minus x. Then you can immediately find that an, all the an's, this is odd times even, so this is a odd function. This is 0 by symmetry. Now I want to compute Bn. So Bn is odd times odd, just like when we compute the integral for the sine times sine. I can get rid of the interval from minus L to 0, so multiply by a factor of 2. So this is 2 over L fx sine n pi x divided by L. So we have recovered the formula before. 2 is f is an even function, which means again that it is 2L periodic, fx equals to f minus x. Then you will find that Bn is indeed equal to 0 by symmetry. But An becomes 2 over L because it's a even times even, this fx cosine thing. So we completely recovered the result for the sine and the cosine transforms, but just by restricting f to be even or odd functions. Any question? 2 is I want to talk about the pointwise convergence. Last time, I assumed that f, the derivative, exists. And so f is continuous everywhere, but the derivative is piecewise continuous. Let me now say a little bit more about the implication of this piecewise continuity feature. If f is piecewise continuous on the interval from minus L to L, one example is the step function you have seen is indeed piecewise continuous. At each point x, I can define fx plus. This one would be the limit of some h goes to 0 plus fx plus h. Means that if I, let's see, I have a function here, and it is evaluated here and here. So this is x. So this is the value fx. So if I take any positive h, it will be here. I take a limit when x goes to 0, and this one value is actually fx plus. Any question? Similarly, I can define fx minus to be limit h goes to 0 minus fx or h plus, but here I use a minus sign. And in this case, this value would be fx minus. Note that it's not necessarily the case that f for a piecewise continuous function, fx must be equal to this or that, because I can define f to be somewhere in between. That's possible. So this is just the two definitions. Now I can state the theorem. So considering the function f, so both f and f prime are piecewise continuous on minus L to L, then for any x in this interval, the infinite term expansion, which is and from 1 to infinity, and the cosine part, we have written this really a lot of times in this class, and the sine part, this one, take the limit to infinity, would be equal to 1/2 fx plus fx minus the average of left and the right limit for every x. So this is for here. And there's also at x equals to plus minus L. This is the boundary. So how do you think about the boundary? You should really think in terms of a periodic function. So on the interval, if I have a periodic function, let's say the function here, this function you have seen before. So for this function, the period is 1. When I think about the convergence of the Fourier series here, you should really consider the value here and the value here. But this value is exactly this thing. So this is gonna converge to, it should converge to 1/2 f. This is minus L plus, and to and L minus. So just like a little bit below here and a little bit positive here. So so this might look a little bit weird. I mean, why do you average them? This is actually quite intuitive. If f is continuous, on the entire R, then this is not a problem at all. Because for a continuous function, the right limit and the left limit, they are the same, but they're fx. So the Fourier series actually would converge to fx for any x from minus L to L, as you have seen before. But if it is discontinuous, all you can do is say, I want to be as good as possible here. I want to be as good as possible here. So you just average them up, and you will find that they actually converge to the middle for this particular point. Any question? So it's maybe a little bit it's intuitive to understand, but the proof is beyond the content of this class. So finally, maybe let me give you one example to do the calculation. So which is fx for this step function 1, 0 from x to pi. For this step function, I want to compute the Fourier series. So first of all, this is an odd function, and therefore an is 0, period. Then I just need to evaluate the bn. So this is it should be 1 over it's a sine, so this is 2 over L, 0 to pi, 1 times the sine nx dx, and this one you just do integration by parts. You'll find that this is 0 if the n is even, and this is 4 over pi n if n is odd. So the Fourier thing, which is, we'll put a tilde here because it's not exactly the same function. This is a Fourier expansion is 4 over pi, and this is sine x plus 1 over 3 sine 3x plus 1 over 5 sine 5x, da da da. And you have seen from the Julia notebook that this indeed converges to the step function, at least within the interior. And for more complicated things, you might need to do more integration by parts. For example, you can try to do the calculation for the absolute value, and that will be very similar to the exercise we did before for the hat function. So let me see. Any question?
I have a question about a previous lecture that we had. So when we were working with the heat equations under both the Dirichlet and Neumann boundary conditions, I'm assuming because because the relationship was defined between 0 and L, we could arbitrarily define the negative side to eliminate whichever basis we wanted. Is that correct?
That's right. Yeah, you mean from minus L to L, minus L to 0, right?
That's right.
Yeah. That, at least that's one way you can think about that. Or you can directly solve the eigenvalue problem for the with respect to the boundary data, and you find that only sine or cosine would survive.
Okay, thank you.
Any other question? So the very last topic we left for the entire semester is really to put all these things together to solve a heat equation. With the initial data and also with some inhomogeneous term. So that's what we're going to do on Friday. We're going to first do that and then briefly review what we did this semester. Okay, so see you on Friday.
I have a question.
Yeah.
How can you just explain really quickly how you like determine like the last step at like 0 is like n even and like 4 over pi n is like.
Oh, you do integration by parts. So it's that you let me go here. So you first do, so this one is a 2 over pi from 0 to pi, and this is d cosine and x. But if you take a derivative, you find there's a -1, there's an n, so we need to have a minus here. Does it make sense?
Yeah.
Yeah, and then you just integrate it out. So this one is further equal to -2 divided by n pi. Cosine n pi is -1 to the -1 to the n, and then this is 1. So you see, if n's even, this is 1 minus 1, so it's 0. If it is odd, then this is -2. -2 times -2 is 4. So.
Okay, thank you.
Any other question?
Are there any similarities between this and a Taylor expansion?
That's an excellent question. Actually no. So this is actually to the opposite of Taylor expansion. So Taylor expansion, what does Taylor expansion mean? So Taylor expansion is really to use derivatives at a single point and then expand around, right? So you compute its first order derivative, second order derivative, and third order derivative, so on and so forth, and you just add them together. You hope that there is a finite convergence radius. And indeed, for some functions, like exponential function, the convergence radius is infinite, and you can expand this to wherever you want. But for many functions, the convergence radius is much smaller, so you cannot use that. Fourier series is a very uses the information in a very global way, because for every term, you actually need to actually touch the value of the function at every point, because you need to know the value of the function everywhere from 0 to L or from minus L to L in order to evaluate this ANs and the BNs. So it's in this sense, it's really to the completely the opposite view of a Taylor expansion. Although for certain functions, they can be either expanded using Fourier or Taylor, but they offer very complementary perspectives.
All right, thank you.
Another question. You mentioned earlier that we should take with a grain of salt that the sine cosine basis that we're using to expand is not actually technically a basis. What were the reasons for that?
The reason is because it's not necessarily a basis for V. So that's also, by the way, an excellent question. So the reason is, what's a basis? In a finite dimensional space, we said that the basis needs to be satisfy two things. One is not too small. One is not too big, means that they're linearly independent. The fact that they're orthogonal guarantees that, so that's good. But also cannot be too small, means that any function in V or any vector in V must be written as the linear combination of this basis. In the context of a finite dimensional space, this is really easy to see, and you just get invertible matrix in the end, you're done. In an infinite dimensional setting, the situation is much thornier because it's not like you take any function fx, I can exactly write it as the linear combination of v. For example, the step function. The step function, if you really talk about in the sense of pointwise convergence, it cannot be written as the linear combination of the sines and cosines because of the pointwise convergence theorem we talked about. I mean, in the end, it converges to 1/2 f to the right plus 1/2 f to the left. And if the function isn't defined like that, it's not, I mean, it's nominally not the same function. But you can see that they must be closely related. That means that you have to define this v more carefully. That is what I mean by taking a large grain of salt. But how do you define these functions in a more careful way? And what do you actually mean by the convergence? This is something you need to learn more advanced mathematics to see what is going on.
Okay, thank you.
Any other question? Okay, see you on Friday then.